As problem found, there was an NA lurking down here on this person right here. So I'm going to delete that. I'm not really sure how I didn't see that earlier. You guys may have seen it when I was taping, and you might have been screaming at the top of your lungs, Doug, Doug. Yeah. Okay. Anyway, so guys, I'm going to start over. Sorta. I'm not going to go through everything. Do a save as for data. Already exists. I'm going to replace it. I want the right one this time. I'm going to go back in and get R. And do it again. But guys, I'm not going to, yeah, I've already illustrated some of that, so. I'm bum-fuzzled now. All right, let's do this. All right, so let's get our data. Welcome to the life of a researcher. All right, guys, there we go. So I want to bring up the, that's really frustrating. I hate when stuff like that happens, but you know, I could have edited it out. You never would have known anything about it, but I think there maybe is actually some value in to you seeing that, or maybe not. Now, I've already shown you how to do this part, except for the prediction success. So, guys, to do the prediction success, you've got to run your model. So let's go ahead and do that. And we have what? Fall status as a function of age plus meds plus open 6, close 6, open 8, close 8. We need total travel. We need total speed. We need react. And we need upgo. All right, so let me make sure that's correct. I don't want any more drama here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so. All right, so summary of our model. And again, we could go through the chi-square and the McFadden's rho as I did before. Now, where I was when all the drama happened was at the prediction success. So let me do that. So the first thing I'm going to have to do is create my fitted values for the model. And what I want to do now is do my library. And I want to do my confusion matrix. All right, so there we go. So I guess, you know, again, I wish it hadn't happened, but then again, I'm kind of glad it did, because you get to see reality. So anyway, our percentage of accurately classified cases will be the number of correct responses. So we had 114 fallers who didn't fall. We had 114 non-fallers who didn't fall, or who were predicted to not fall. And we had 34 fallers who were predicted to fall. We want to divide that by our total sample. So our percentage of accurately classified cases is 60.2%. Now again, you might say, well, why is this different than what you published? And again, the reason it's different is because for some reason I didn't get rid of the other two of the other measurements when we published this. All right, guys, sensitivity and specificity. We should know by now that we can take 34 divided by, what is that, 105. So 0.32, that's going to give us our sensitivity. And we could take 114 divided by 141. It's going to be off a little bit, but 0.809 would be our specificity. Okay? Now, the next paragraph we get into table 6. And I do know you start counting at 1 and not 6, but you got to remember this is taken out of the descriptive statistics, which had tables 1 through 5. So what I've done here is I've done the regression coefficient, the Wald statistics, odds ratios. So what I did here in this table, and what you will do, is really just copy the estimate. So the estimate right here is the beta. The Wald Z ratio is your Z value. The odds ratio, I'll show you how to find in just a second. And the p-value, of course, is the value in the last column. I always put my constant last. So really all I need to do is show you how to find your odds ratio. And if you remember, that's just e raised to the beta. So we just need to take each one of these values and raise it, or take e and raise it to each one of these values. Gives us our odd ratio, and then I'll show you how to create the 95% confidence interval for your odds ratio. So guys, turns out that's very easy. So what I'm going to do now is create the odds ratio. And just to show you that, right up here, if we look at this, let's get one that's, let's look at UpGo. UpGo is 0.062803. So let's create that. So I'm going to look at the coefficients of our model, and you're going to see 0.0628, which is what I just pointed out. Now I'm going to exponentiate that. And what you'll get here is you get the odds ratios. So those are the values that are put in this column. And then to get the 95% confidence interval, what I'll do is I will do EXP, the confidence interval of our model. Okay. So you notice that the upper bound on the intercept is freaky high. It's even much higher than what I had right here. We don't worry much about the intercept, but so just go ahead and report that. So guys, these values right here, EXP, coefficient of our models, these coefficients are our betas. And again, they're off a little bit because I have a different sample size. These EXP coefficient of our models are odds ratios. And then the confidence intervals for the odds ratios are here. Right there and right there. All right? Now, the next thing I did is I came in and I did a standard logistic regression model followed by a backward elimination regression analysis. So, guys, the way you do that is you're going to create a backward model. I'm just going to call it backward because I don't really know anything else to call it. And I'm going to use the step function. So I'm going to take my original model and I'm going to do a direction because there's something that's called I was going to tell you there's a forward elimination and trace equal false. Now, let me tell you what's going on here. First of all, we're creating a new model. We'll go through these steps that I talked about these iterations, this algorithm, so to speak, that I talked about earlier. We start with our initial model. We tell the direction that we want to go, so we're using the backward. And trace just says we don't need to see each step. We just need to see the model we started with and tell me the final product, the final model. I don't need to see, well, what variable was taken out after step 1, what variable was taken out after step 2. If you want to see that, then you change false to true. So now I can just do summary of my backward model, and you'll see that according to this algorithm in R, age, open 6, close 8, and upgo give me just as good a model, probably even better than the original model, which was model. So this backward model is as good or better. And you got to think about it. If you can predict at the same level, the same classification accuracy, with only 4 variables versus 10, you would want the smaller model because it's just easier to manage. Plus, you don't get into situations with collinearity and multicollinearity, highly correlated variable predictors. It's not as likely. So, and we'll talk about that a little bit more in just a second. So, beginning with the full set of predictors, after 4 scoring iterations, a statistically reliable model emerged. Now, how am I going to do that? Well, guys, I'm going to do that just like I did before. I'm going to do the walled test. So I've got to do my library, and then I'll do the walled test. And I want B to be the coefficient, but this time I want the backward. And then I want my sigma to be variance covariance of the backward. And then my terms are 1 to what? Well, I have 5 terms. So you can see that the model is easy for you to say. It's statistically reliable, and it's not a lot different than what we got up here with the 2 extra cases. So the variance accounted for in false status remains very small. Guys, I'm not going to do this again because I showed you how to do McFadden's rho. And now I want to do prediction success. So let's do that, PAC. So guys, remember to do percentage of accurately classified cases. I need to do the confusion matrix. Well, guys, I need to, let's just do backfitted. Losing my mind here, people. We did call it backward, right? Yeah. Okay, so let's do confusion matrix. And we want fall status over backfitted. Threshold equal 0.5. All right, so classification accuracy in this is going to be equal to, what do we have, 122 plus 31 divided by 122 plus 74 plus 19 plus 31. So percentage of accurately classified cases decreased a little bit, right? 60. Let's see. No, actually, it actually went up. So guys, I think you can see that we've got a better model after the backward elimination than we did with our full set of predictors. So what I do next is I come in and I talk about that, and then I come in and talk about prediction success, and then I come in and talk about the variables that emerged as statistically significant. And then I come in and make a brief statement about sensitivity and specificity, and they remain relatively unchanged. And you can do. I'm not going to do that because uh, you guys should be pros at that by now. So guys, again, the walled the beta is going to come from your estimate. The walled z ratio is going to come from the z value. The odds ratio, how are we going to do that? Well, we're going to do it just like we did before. In fact, I can go back up and get that right there. Oh. What am I doing here? Losing my mind. All right, so then I can find the XP of the coefficient of backward. So those are the values that, yeah. And then the confidence interval. Will be right here. So that's what goes here. All right, so since the 3 predictor model was statistically reliable, whereas the 10 was not, and the percentage of accurately classified cases actually increased moderately, the latter model was used to determine cut points for adequate sensitivity and specificity. So a receiver operating curve has been shown, yada, yada, yada. So you can read all that. It's presented in graph 1. That's found in that the ROC analysis could be extended for use in visualizing and analyzing behavior diagnostic systems to test the accuracy using the area under the curve. For the set of predictors, the area under the curve was found to be 0.61, which indicates a poor accuracy classification. Easy for you to say. All right, gang, so what I want to do is I want to show you all the work we got to do to find graph 2 and graph 3. The easiest way to get your ROC curve is to use what I taught you in the previous video. And so let's bring that up. Well, guys, I'm not going to do that because I showed it in the previous video. You can go back and look at that. So finding the this ROC curve is easy to do. Again, I showed it to you in the previous video. But what I want to show you how to do is the madness that it takes to look at a plot of the model sensitivity and specificity for various cutoffs. Find the cutoff, not necessarily 0.5, which we've used previously. It's going to look at the specificity and sensitivity based on a variety of cutoffs. In fact, the cutoffs are going to range from 0.2 all the way up to 1. And it's going to look at where we maximize the difference between, or I'm sorry, where we minimize the difference between the two values. So, guys, I'm going to show you how to do this. It's a lot of stuff going on. I put up on, because I don't want you to type all this stuff. I put up on Blackboard a cut point code, and what we want to look at right now is we want to look at the stuff from here down. So the very first thing I'm going to need to do is I'm going to need to install the packages optimal cut points. Next thing, I'm going to access the library. So there's a library for optimal cut points. Next thing I'll need to do is install another package. No, wait a minute, where am I? Install ROC. Okay. All right, gang, and we are ready to go. All right, so again, if you're playing along over here, where I am is right here. Now, the first thing I need to do is I need to take this, copy it, paste it. And I tell you, I came up with most of this code on my own. It took me forever to write this, but I did steal some of this, and I wish I knew the person's name so I could. But anyway, I've lost the source where I got some of this, and I wish I could give him or her credit. So if you're out there, I'm thinking of you, but I just lost I lost it. So what I'll need to do here is set up what I call predict or pred 1. So I want the fitted for the backward. Is that what I called that? Yeah. And I want from data, because I want this to be false status. Next thing I'll need to do So guys, I'm making this easy on you. I was going to be ornery and make you just type it all out for you and make you type it yourself, but I thought that was kind of ugly. So next thing we'll do here, I wish I could make that larger, and I can. Next thing I want to do is I'm not going to copy paste this. So no, next thing I want to do is, so you can see that X name is going to be our true negative rate, Y name is going to be our true positive rate, alpha will be our cutoff, and X values list of 1. I think it's pretty clever the way this worked out. Next thing I want to do is stats 1 at alpha values, and I need to do 1. Now I want to see the ones of those that are less than or equal to 1. So instead of typing all that out, I'm just going to, and I hope you're not getting impatient with me, but this is really cool. I'm actually pretty proud of the stuff I did here. Okay, next thing I want to do is I want to do a plot. And make sure I've got everything set up correctly. Yes, that looks good. And okay, I want the ab line, so that's not giving me exactly what I want. Let's come in and okay, so this is the sensitivity and specificity, and then we'll eventually come in and put a vertical line to find the value that actually gives us our minimum threshold. So guys, to do that, we're going to start setting this up. So which min? So we haven't got our final graph just yet. So stat 1 x values, AB is absolute. Okay, cool. This is what we want. So guys, 121 is a number that I need to have on my radar. Now I got to change this to match the number that I get from which men. Let me show you what happens if you put something else there, like 123, what it was. It gives you the wrong numbers when it does. So we want 121. We want to get the right number. It's not off by much because not much difference in 123 and 121. Next thing I want to do is set up stats 1. Does anybody yet know what these values represent? Probably should when you see this because 0.57. Let's go back over here. What do you think is what? Anybody got it yet? You got 3 values, 0.41. Well, no, this one, forget this one right here. But we have 0.42 and 0.57. So guys, those are the values of the sensitivity and specificity. And then we need to find the value of the threshold, which we can do. Isn't this cool? I mean, seriously. Sort of. A little bit of credit here, people. All right, so we're going to plot. So let's go out here and get all this stuff. I literally spent one of my Christmas breaks, spent almost the entire time coming up with this. All right, gang, there you go. So the it looks like okay. I'm off a little bit here. So the value, okay, the value of the threshold turns out to be about 0.562, where the sensitivity and specificity are actually the minimized difference holds. So guys, what you do is you'd copy this, insert it into your document, and so you'd have graph number 2, the plot for various cutoffs. Seems like something is missing here because we should have the stats 1 alpha values, y values. There should be an x values. Should be yeah, okay. That's what was bugging me. So to find the stats 1, the x value is where, well, it makes kind of sense because it's the x value on your graph. That's where the cutoff is that minimizes this difference. Okay, and again, you might say, well, the minimum difference of these values is where it crosses. Again, it's not a metric that we're necessarily familiar with. It's kind of a different algorithm to find the cutoff that, according to the way it defines minimum difference, the cutoff that makes that happen. So you've got the sensitivity, specificity, and then the x value down here is where the let's see. Yes, the x value is the value of the threshold that achieves this minimum difference up here. So, gang, I am done. You don't have to know the theory behind this stuff. You just really need to be able to replicate this. Some of this stuff will be on your second assignment, which will be posted pretty soon. So, guys, that's all I got. Take care.